Hi, my name is Tim McDevitt, and I'm going to talk about vector visualization. I apologize I'm not able to be there in person to give this talk live, so this has been pre-recorded. So in version 12, we made a lot of changes to existing vector plot functions, and we've also created some new ones. I'm going to basically review a little bit of the changes to the old functions, and then I'm going to spend most of my time talking about Streamplot 3D and these two displacement plots. So here we have a comparison. I tried to recreate what the old vector plot used to look like and what the new one looks like. So obviously the old one has some differences. It was all monochrome. The vectors were scaled by the magnitude of the field. And the points were selected for the vectors based on a regular rectangular grid. In the new version, the arrows are colored, and they're colored by the magnitude of the field. They all have the same length, so that gets more sort of color on the page. And then there's also a hexagonal packing there that fits more arrows into the same area. And I think generally has a better visual appeal. One thing I want to point out is in most of these vector plotting functions, whatever sample points you use for your plotting, the arrows are centered on those points. Okay, so in the picture here, you see red dots. Those are the sample points, and then the corresponding arrows are centered on those red dots. And I bring this up because when we get to vector displacement plot, we're going to deviate from this convention. So I want to highlight that for you. We have similar changes to vector plot 3D and slice vector plot 3D and so on. I'm not going to dwell on that for lack of time. We also created complex vector plot, complex stream plot. So if you have a complex function of a complex variable, you split it into its real and imaginary parts to make a vector field, and that's what complex vector plot shows. And then complex stream plot shows the corresponding sort of streamlines. All right. And again, I'm not going to dwell on this because this is a little bit older. Now, vector plot and stream plot have both been in the language for some time. Again, what vector plot does is it takes a vector field, chooses a sample of vectors in the field and plots them. And then stream plot solves a corresponding system of differential equations and plots a sampling of those solutions. So for this vector field here, you can see the vector plot on the left and the stream plot on the right. They have a similar visual appearance. They give similar information to you, but the one on the right is a little bit smoother. And people have been asking for a similar function in 3D for quite some time. So that's what I'm going to be talking about here for the next few minutes. Now, before I do that, let's just look at a classic example of a use for either stream plot or vector plot. So this is a dipole field for 2-point charges according to Coulomb's law in the plane. So they have opposite charge. And so you can see these sort of lines in the field going this way. Okay, so the picture on the left has a lot more color in it. And the reason for that is in the stream plot, the sampling of points gets very, very close to the two poles. And so the sampled range of field magnitudes is very large on the right. And that has the effect of basically compressing all the color down to points very, very close to the poles. And so you don't see the color. Now you can address that with some options, but this is what they look like by default. So I want to show you this in 2D, and I'm going to show you a similar thing in 3D here in a minute. So vector plot 3D has been in the language for a long time. Stream plot 3D, though, is new. Again, vector plot 3D is going to sample vectors in a field and plot them, and stream plot solves these corresponding differential equations. So here we have a side-by-side comparison. So again, vector plot we've upgraded in version 12. And here is what stream plot 3D looks like for the exact same field. So I think it's a little easier. This is just my opinion. I think it's easier to follow the flow in the stream plot 3D, that is. It's a matter of opinion, but I find it easier to follow. The colors of the streams indicate the magnitude of the field at each point. So there are a lot of options. I'm not going to go into them all, but I think stream markers is worth sort of pulling out by itself. So for this simple vector field here, I'm going to show you these different stream markers. So the default is line. If you want a more 3D appearance, you can use tube instead. Ribbon and arrow ribbon are both nice if your field is twisting or if the flow is twisting and you want to show that. Now the ribbons don't show the direction of the flow, but the arrow ribbons do. And so you can see these are all sort of flowing upward. And then we still have arrow and arrow 3D available as well. Again, there are a number of options for Streamplot 3D. These are going to be familiar to anyone who's a user of Streamplot. So I'm plotting over a cylinder instead of a cuboid, change the color, add a legend, downsample the points so the image isn't too busy, style the lines, and then change the region, the color of the region. So these are all familiar options. I'm not going to dwell on those. Okay, so here's a standard application. In 3D, we have a dipole field, just like we had in 2D. Here's what the vector plot 3D looks like. Okay, now it's very busy. That's unavoidable because there's just a lot of arrows there. There's a lot going on in 3D there, so it's very hard to see what's going on. But I think the stream plot makes it much easier to see what's going on. Okay, you can actually see the field lines. The color is washed out for the same reason we mentioned before, but that can be addressed with a region function. So here, the region function takes, for Streamplot 3D, up to 7 arguments. The first 3 arguments correspond to X, Y, and Z in the domain. The 4, 5, and 6 arguments correspond to the components of the vector field. And the 7th argument, or slot 7 here, is the norm of the field. And so what I'm saying is only plot points in the streamlines where the norm is less than 5. All right, and so I added the legend here so you can see it goes up to 5. And then you can see that recovers a little bit more color range, but you can see that all the color change is confined to regions near those 2 poles. Okay. Now, another thing I like to do is basically use Streamplot 3D to make a vector plot 3D. So basically, these are the same field, but what I've done in the second case with Streamplot 3D is I've changed the markers to arrow 3D, and then I've changed the stream scale here so that there are 2 points per marker, and then the 0.075 controls the magnitude. So basically, these are just arrows of the kind that you see over here. The difference is the sampling over here is done regardless of what the field is. All right, it's just done systematically over a hexagonal packing of points in that cube, whereas on the right, they're sampled along the solution curves. And so I think this picture is easier to understand than this one is. So applications for Streamplot 3D, the natural one here is for visualizing solutions of autonomous ODEs. Autonomous just means that time doesn't appear on the right-hand side. And so here you just put in that field and you get a sampling of solution curves. I downsampled the stream points so that it wouldn't be too busy. Now, one thing you can't tell is what direction the flow is going. So again, you can mess with your markers. So I changed it to arrow and I made stream scale full. So what you get are long arrows that indicate the direction of the flow. You can use this for more specialized cases, like here's the Lorentz field. And then I just picked a single starting point at 111, which is in the middle here somewhere. And so you can see the resulting trajectory gives us a sense of what the Lorentz tractor looks like. Notice that we integrate both forward and backward in time. So the starting point is not this point out here, it's in the middle somewhere. You can also visualize solutions on a manifold. So if you solve the differential equations corresponding to this vector field, you find solutions that live on spheres centered at the origin. And so if I take my stream points to be points on the unit sphere, then I get curves that are confined to that unit sphere. In this case, if you solve the corresponding differential equations for this field with this initial condition, then you get what's called a twisted cubic. And this is something that students are introduced to in a course on multivariable calculus. And so by showing the curve as a ribbon, you can actually see how it's twisted. And you can see that the maximal torsion occurs at the origin, or at least close to the origin. Now, vector displacement plot is very different. All right, so let's just look at the example here. So what you do is you have your variable specification, so -1 to 1, -1 to 1 in both directions. And so that gives you that gray square in the background. That's the reference domain. And then the field is a displacement field that tells you how any point in the reference domain deforms under this transformation. So the color indicates the magnitude of the field. Now, this highlighted field here is really a 90-degree rotation along with a dilation by a factor of square root of 2 in every direction. All right, and so you might say to yourself, well, all right, a couple of things. First, there's no vectors. And second, that doesn't look like a 90-degree rotation. So I'm going to come back to the vectors in a minute. But the reason it doesn't look like a 90-degree rotation is because we are scaling the displacements so they are neither too big nor too small by default. Okay, so I think a really important use case for vector displacement plot is for problems in solid mechanics where you'll have like a steel body or a concrete body or something like that, and you put forces on it, and you want to see how the body reacts. So the displacements there are going to be microscopic. They won't be visible at all, right? And so we're going to amplify them so that they're actually visible, right? And then, the other direction, if the displacements are too big, we don't want the picture to be distorted. So we're going to scale everything so the 90-degree angle here doesn't look like 90 degrees. Now, where are the arrows? Well, they're not there by default, but if you specify vector points, then you get arrows. All right, now these arrows are different than in most vector plotting functions. So what happens here, instead of being centered on sample points, like this, if we focus on this arrow, its tail is at its position in the reference region, and then the head at the corresponding point in the deformed region. Okay, so these arrows go before, after, undeformed to deformed, point by point. And again, since this is a rotation, the vectors get larger as you move away from the origin, and they're actually 0 at the center. Okay, and also the colors you can see sort of work their way out in concentric sort of rings from the center. Now, one thing I like is specifying just the vector points on the boundary, because it gives me a similar sort of feel as the previous picture, but the picture is not as cluttered. Now, again, the displacements are automatically scaled. Okay, so I'm taking that same vector field and I'm multiplying it by 1,000,000, and here I'm dividing it by 1,000,000, and you can see the plots look the same. So we don't want really big or really small displacements to look really big or really small. All right, but there may be times when you want to see that the displacement really is a 90-degree rotation. So all you have to do is say vector sizes goes to full, right? And now you can see clearly this has been a 90-degree rotation, and you can see it's a dilation by a factor of square root of 2. So for example, if you start here, you go over 1, up 1, that diagonal has length √2, and now here it has length 2, so it must be a dilation by √2. All right, so if you want everything to scale, that's easy to do too. Now, the field is typically the field magnitude is used for coloring, but you might want to color by something else. So in this case, I've chosen to use sine of 5 pi xy, and you can see that has changed the way the field is, the deformed region is colored, but it's a little grainy. So the use of plot points just smooths that out. Okay. Now, the last thing here, you can see the reference region in the background, or mostly just the boundary of it here. So you might want that, you might not want that. If you choose to not want it, what you do is you just suppress its filling and boundary styles, and then the reference region will be gone. Okay, so these are some really nice ways you can modify the appearance of these plots. Another thing I think is great about vector displacement plot is the flexibility in the domain specification. So again, this sort of domain specification is familiar to Wolfram language users, but you can also specify a graphics primitive, a union of graphics primitives. You can specify a line. Okay, so it's a one-dimensional curve, but it's embedded in 2 dimensions, so we can show its displacement. You can use an implicit region. You can use a mesh region, boundary mesh region, a parametric region, that's a curve, or a parametric region that is 2-dimensional, right? So this kind of flexibility is really nice when you're, say, working with problems that involve finite elements or something like that. You're not restricted to rectangular domains, which is really nice. Okay, so some applications. So something you talk about in a linear algebra class is simple linear transformations. So we might talk about dilations, contractions, shears, and rotations. So what I've done here is I have taken and added a texture to my deformed region. I am showing full displacements, okay, so nothing scaled. And I have suppressed the boundary of the deformed region, and I have removed the reference region. Okay, and so here I have a dilation matrix, I have a shearing matrix, and I have a rotation matrix. And I have to subtract the identity because we're giving displacements here, not the deformation. Okay, so you have to remember to subtract the identity. So let's start from scratch. So here you can see the texture applied to the deformed region. I can spin it. I can shear it in the X direction. I can shear it in the Y direction. And I think it's nice for shear to include a mesh because you can see the change in angles between the lines in the mesh. You can also dilate horizontally or contract horizontally. If the factor is less than 1, it's a contraction. If it's bigger than 1, it's a dilation. And then you can also dilate vertically. Okay, so this is a nice way to sort of illustrate something that is typically talked about in a first course in linear algebra. So again, I think a really important use case here is solid mechanics. So here we're going to look at a couple of simple examples. The first one here, you have a bar of length 2L and height 2H, and you're going to apply these moments on the ends of the bar. I'm going to assume the material is as simple as possible. It's linearly elastic, it's homogeneous, and it's isotropic. So there's two material parameters to specify. There's Young's modulus, which basically indicates the stiffness of the material, and then Poisson's ratio. And then here I'm indicating the magnitude of the applied moment. And so you can actually solve this problem for the displacement field. So it's really nice. But one thing I want to point out to you is this coefficient is really small because m is 1, so the numerator is 3. And this Young's modulus is 3 times 10 to the 7, right? And this is a big number. So this highlighted coefficient is really small. So the displacements are really microscopic. So I mean, think of this being a steel bar. You apply this moment on the ends, you're not going to be able to see the displacement, at least not to the naked eye. But if you do vector displacement plot of that, it is bent. So you can actually see the idea of it, but it's not to scale. Okay, and again, the coloring here is by the magnitude of the displacement. So 0 displacement here and here, and maximal in the middle. But if you set vector sizes to full, this means no scaling, right? And so you can't see that it's deformed, right? It just, the deformation's too small. Okay. Now you might say, well, look, I can see that it's bent visually. So maybe instead of using color there, I could use something else. So there's a single non-trivial stress component here. That's the normal stress in the X direction, which has a nice form. And so I can use that here to color the bar. All right, and where that stress is positive, the material is in tension, and where it's negative, it's in compression. So it's in tension up here at the top and in compression on the bottom, which I think makes sense. Another slightly more complicated example is that of a stress concentration factor. So imagine you have an infinite thin plate. So this is supposed to be infinite. And there's a hole at the origin. Now, it doesn't matter how big the hole is. Okay, it says radius A, but it doesn't matter how big it is. Right? So there's a hole centered at the origin, and you're going to pull on this plate. So what happens is the stress actually gets concentrated at the top and bottom of the hole. And this is important from an engineering perspective because if whatever load you're applying, you're going to increase that at the top and bottom of the hole, and that could lead to cracking or material failure or something like that. So I've suppressed the math here, not the math, but the code. It's not huge, but this is what the displacements look like. It's not huge, but it's big enough that maybe we don't want to look at it. Sorry, I've hidden it for myself now. Yeah. So if you look at this, away from the hole, there's not a whole lot changing. Okay, but what you're looking at here is the hoop stress, which is sort of it's a normal stress in the angular direction around the origin. And so you can see that there's a maximum of 3. Okay, this is the stress concentration at the top and bottom of the hole. Sorry, so whatever the applied tensile load is to the outer edges of this plate, at the hole, you have a factor of 3 times more stress. Okay, and again, this could be really important in practice. Down here, we have an indication of points that are in compression down here. All right, and so this is something that you might cover in a course in elasticity. But one thing I had never really seen was this with arrows on it. So when I drew this with arrows, a little light bulb went off in my head. Like, it really helped me build my intuition. So the origin is here at the center of the hole. And then the vertical axis, the y-axis, goes up this way. So what this made me think about would be if you had 2 points at the top of the hole and one just to the left of the y-axis and one just to the right, the arrows that would come out from them would be, those points would be pulled up, and then the one on the left would be pulled left and the one on the right would be pulled right. And so they give me this intuitive feeling of sort of pulling the material apart there that I didn't fully appreciate before looking at this picture with the arrows in it. And so this really helped me build my intuition for this problem. And it could perhaps be helpful in other circumstances as well. Now in 3D, we have vector displacement plot 3D. So you give a 3-dimensional field, right? And then here just giving a cuboid reference region. So you can see what this looks like. And if I do vector sizes full here, you can see actually the deformation is not as big as the scaling makes it look, okay? But that's okay, that's what we intend. You can include vector points. It doesn't make a whole lot of sense to include them on the interior because you can't see them on the inside, but on the outside, it can be helpful to appreciate what's going on with these vector points. And again, vector displacement plot 3D also has impressive domain flexibility. So here we have a domain that is a graphics primitive. Here we have a region difference of 2 cuboids. So, a difference of 2 primitives. Here we have a curve. Here we have an implicit region. Here we have a mesh region, boundary mesh region. And again, this is really useful for interacting with finite element code. Parametric region where the region is a curve. Parametric region where the region is a surface. So again, a lot of flexibility in terms of domain specification. So a couple of examples here. What we have is an elliptical cylinder here with semi-minor and major axes A and B. We're going to apply a torque to the top and bottom of this elliptical cylinder. You can solve for the displacements in nice closed form. T is the applied torque, the magnitude. Mu is the shear modulus in gigapascals, let's say. And so, it's polynomial, right? With some constants running around. And in this case, I think it's really nice to use a mesh to indicate the twist. So you can really see what's going on there with that mesh. And there are 2 non-trivial shear stresses. So to me, it makes sense to maybe color by one or more of these shear stresses. Alternatively, you might combine them, like compute like a von Mises stress or something like that. But this, you have the flexibility to do that. And then sort of the big example, I did not make this example, but I think it's a really nice illustration of vector displacement plot 3D. So here we have is a spoon. This is actually a boundary mesh region. You can't tell that by looking at it, but that's what it is. And we have 3 displacement variables. These are dependent variables and 3 independent variables. These parameters here, these are the material parameters, the Young's modulus and Poisson ratio. And then you call in dsolve or ndsolve value. And then we have these new tools for doing solid mechanics. And so you can see here we have a load applied at x greater than or equal to a 10th. Okay, so if we look at the actual, point of this example, x bigger than a 10th, the load is applied sort of on the scoop part of the spoon in the downward direction. And then we have a fixed condition for x less than minus a 10th. So at the tip of the handle, this thing is prevented from moving. Right, and so physically that's what's going on. And then vector displacement plot gives you a very nice illustration of the deformation of the spoon, pretty painlessly. Okay, now I'm just about out of time, so I just want to introduce the 2 list versions of these functions. So list vector displacement plot is very similar, except instead of putting the vector field here, you put in the data that represents the vector field, okay, and then your domain. And similarly in 3D. So you put in your data representing your vector field, and then your domain. And that, by doing so, you get out a similar sort of output. Okay, so again, I apologize for this being pre-recorded, so I'm not there to answer any questions. If you have questions, please feel free to email me at timothym@wolfram.com, and I'll be happy to try and get back to you. Thank you very much.